Hi, everybody. This is Mr. Folly, and welcome to video 3, Big Idea 3, our third video. We're going to talk about the kinetic molecular theory, which is one of the big explanation things that we use a lot. All right, so first of all, it's a kinetic molecular theory of ideal gases. So gases are treated like ideal gases. Now, ideal gases don't really exist, like the ideal person doesn't exist. So in chemistry, we treat everything as if it's ideal, and we try and focus on things. A very common question is, what's the most ideal gas? So if you think of your ideal boyfriend or ideal girlfriend, maybe they're tall or maybe they're brown-haired or something like that. But that doesn't mean you're going to get everything you want in your ideal Friday night date, okay? Characteristics of ideal gases. The particles are point masses. So remember in math class, a point has no volume, okay? It does have volume as a group, okay? So that means you don't worry about how big the other ones are. So again, this is false, but it's a good estimation. So my example of this is if I'm trying to put people into a car. This is my car. I learned how to draw in physics class. Can 9 people fit in a car? Well, it depends. How big are the people? Are they babies? Then it depends. But could 9 ants fit in a car? Head, abdomen, thorax, antennae. Woo. Yes, right? 9 of the biggest ants in the world can fit into a car. You don't have to worry about it because they're so small. Okay. Another characteristic of ideal gases is that particles move in rapid, random, straight line motion. This is directly proportional to speed to Kelvin temperature, not Celsius nor Fahrenheit. Okay, so we can use this as a comparison for speed. Now, in reality, and I saw there's one question that gets caught up in this, kinetic energy, yay physics, is 1/2 mv squared. So it's directly proportional to speed squared to Kelvin temperature. Okay, for our purposes, usually if it doubles, and all that stuff. Okay, collisions are perfectly elastic. So what this means is I've got a gas particle going. And if you think of a pool ball, so if you're in shooting a little pool, and you got your little 8-ball singing your what is that? Zach Bryan song, "We're shooting with an 8-ball," and it bounces and bounces and stops. Right? So it bounces and bounces and stops. That's not a perfectly elastic collision. The ball would keep going and going and going and going. Okay? So collisions are perfectly elastic in ideal gases. Okay, this is false, but a good estimation. It loses very, very little particles. What this means is gases don't get tired and settle down to the ground. Okay, particles are unattractive to themselves and the container. There's no London dispersion forces. There's no dipole-dipole. There's no attractions. The attractions are so small, we can just treat them like they don't exist at all. Okay. We can maximize the ideality of gases. Remember how this is very close, but we want to make it as close to the truth as possible. If we have high temperature, the collisions will be more elastic. So if it goes faster, boom, boom, boom. If it goes faster, it'll bounce better. If I throw a ball against the wall softly, well, if I throw it hard, it bounces closer back to me at the same time. Okay. A higher temperature also reduces attractions. So if you're zooming by, if I'm a particle going boop, 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 and here's another particle going boop, 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 and we would be attracted to each other, we go, ooh, ooh, and we change our course. Now, if I'm a particle going, wow, so fast, wow, so fast, then there's not going to be an attraction because they're zooming by too quickly. Okay. A large container. If there's a large container, the actual size of the particles become less significant. So notice how if I wanted 9 people, the size of that to be insignificant compared to 9 ants, maybe I would say in a skyscraper, or 9 people in an enormous cruise ship. Okay. And the attraction would be weaker because the size is larger and it's farther away. Okay. Oh, it says Riley. That wasn't Riley. I forgot who had a Jeep in our class. Somebody had a Jeep. I think it was Lola had a Jeep. Low pressure. If it's low pressure, this means there's fewer particles or a larger space. So the actual size of the particles matter less, and the attractions would be less because you're farther away. Comparing ideality of substances under the same conditions. So the most ideal is a smaller particle, and the most ideal has the weakest attractions. And then we'll do problem number 1984, A and B, and we'll see where it is. Temperature. Boltzmann diagram. Here they are again. Boltzmann never goes away. A Boltzmann diagram is the proper distribution of energies based on temperature. You need to be comfortable with this. This is cold. This is hot. Okay? And hotter is righter and lower. Okay? The area under the curve would be the same. A vertical line, so a lot of them say, okay, there's a vertical line right here. Anything to the right of the vertical line would evaporate. So in this cold gas, some of the particles would evaporate. On the room temperature gas, many of the particles would evaporate. And on the hot, well, I guess would be gas, the hot liquid, most of the particles would evaporate. I know they say gases, but it's typically a liquid. It could be a liquid or a gas, but you get the idea. Okay. Not every particle has the same energy, right? If you've got a temperature, that's the average, right? So if our average is 88, that doesn't mean everybody has an 88. There's some 99s, there's some, 79s and all that. Heating it shifts righter and lower. So notice heating it shifts righter and lower. Cold to room temperature. Room temperature to hot, righter and lower. Okay. Temperature is a measure of kinetic energy. And again, we see 1/2 mv squared. Kinetic energy increases with more velocity or more mass at the same velocity. The same temperature means the same average velocity. Lighter particles move faster. Hydrogen is faster than NH3. Okay, AP weirdness. And the love of whooshies. More whooshies means that it's faster. So do you see how this has a bunch of whooshies? And this has fewer whooshies? That means this is fast. And this is slow. Okay. And that's it. So, hey, 7 minutes in and out. I hope you're enjoying your 4-day weekend. Toodles.